Okay, so thank you for the introduction, Dan. Good afternoon, everyone. I'm Jerry Casiez from the University of Lille. And I'm going to talk about end-to-end latency and how to measure it. So end-to-end latency, or lag, of a graphical user interface is defined as the duration between a user action, so typically the movement of an input device, and the corresponding on-screen visual feedback. So here's the cursor movement. So the most common procedure to measure end-to-end latency is to use an external camera to record both the input device and the associated response on screen, and then to analyze the video to match two related events in order to count the number of elapsed frames between them. So this is a tedious and error-prone process just to do one measure. So what we would like is a lightweight method to measure end-to-end latency in real time, the possibility to perform multiple measures per second to measure the variability of latency, also called latency jitter, the ability to insert probes at different levels of the system to understand where the latency comes from. This is very difficult just using an external camera. And last, no hardware hacking, just use the tools you have on your desktop. So what we propose is to measure end-to-end latency by positioning a standard optical computer mouse at a fixed position on a monitor, so you do not move the mouse. And then we display a given texture on the screen and move it of a controlled distance. So the texture displacement is intended to produce fake mouse displacement at a given and measurable time, which will thus be detected and reported by the mouse sensor to the system as normal events. So we know when we move the texture on screen, and we know when we get the mouse move event. And in this way, we measure the end-to-end latency. So the key problem to do that is to find the correct texture to display. So we first try to display and move different textures designed on the rule of the thumb, like grids, different kind of grids, some noise, Perlin noise. We even tried some images, and most of the time it did not work, so we really needed to better understand what was going on. So for those of you who do not know, a modern computer mouse consists of a small camera comprising a pixel array, typically between 20 by 20 to 30 by 30 pixels, a lens, and an LED or laser to illuminate the surface. And the camera has a high frame rate, typically between 2000 and 12,000 Hertz. So we retrieved the raw image from a mouse sensor by connecting it to an Arduino board. And in this way, we obtained the physical dimension of the area recorded by the sensor, which are around 1 by 1 millimeter. So on a 100 pixel per inch screen, this corresponds to about 3 by 3 visible pixels. And that gave us the size of the unit pattern to design our texture. So the other thing we noticed is that when you position a mouse on a white display, the sensor can actually see the pixel grid, also known as the screen door effect. So the screen door effect is visible when you look at the screen closely. And so you can see a physical gap between pixels corresponding to this black region. And in fact, this is something really critical to find out the correct texture to display. So we do not know exactly what are the algorithms inside the computer mouse. but it is likely the optical sensor does some image processing to detect common features between successive images to compute the displacement. And this detection of features is likely to rely on contrast detection. So the sensor can not only detect features between large black and white regions, but also on the scene regions corresponding to the pixel grid. So when we display a texture and we move it, so what we would like the mouse think happen is that the whole texture moves, including the grid, but the grid remains fixed. So what happens is that from one image to another, when we move the texture, so the pixel grid remains fixed, and when the mouse computes the features, so what we would like to do is that whole features move, but it's not what happened. What happened is that most of the features are incorrectly classified as stationary, so the mouse does not report any event. So to design the right texture to display, so a few rules. First, the more adjacent white pixels there are, the more the screen door effect is visible. And if you have a pair of adjacent white pixels, the black gap between the pixel is apparent. So we need to mix the black gap between pixels with black pixels so that it is no longer perceivable. And so we need to hide the screen door effect. So with such textures, so when we move the texture, in fact, only a few features are incorrectly classified as stationary. And so this is the texture we used. As you can see on the right, from the image sensor, the grid is no longer visible. And so we evaluated all possible pattern with 3x3 pixels unit pattern. So it's not the only texture that works, but previously I've given you the rules to design that texture, but this one works pretty well. So we are happy we have our texture to display and to fake mouse displacements. But there is one thing that remains to do. So when you move the texture of one pixel, it is likely to produce mouse report as low as 1 count. And we have to make sure that 1 count reported by the mouse produces displacement of the system pointer of at least 1 pixel to have a mouse move event. So in the paper, we detail how to tune the transfer function in the mouse configuration panel for each system in order to get 1 pixel displacement for 1 count. I mean, at least 1 pixel displacement of the system pointer for 1 count coming from the mouse. So this is basically the only thing you have to tune when you want to apply our method, is to change the transfer function setting in the mouse configuration panel. We evaluated the texture with 10 different optical mice and with 2 monitors with different resolutions. We have a normal 90 pixel per inch monitor, and we also evaluated an Apple Retina display with a high resolution. And except 2 mice that do not work at all on each monitor, the other mice show a success rate above 16%, which means it's possible to perform at least 1 measure of latency per second using these mice. And here the average latency is close to 70, is around 70 milliseconds on a high-end machine. We also measured end-to-end latency at different positions on display. Note that all these positions were not measured simultaneously. And considering that LCD monitors usually update the screen from top to bottom, first it makes sense to get lower values for the top of the screen. And if we subtract the mean latency at the bottom of the screen and at the top of the screen, we get 16 milliseconds, which is close to the time screen period. So the nice thing about our technique is that we can also insert probes in the system. So our probes consist of callback functions registered at different places. We start measuring time before the texture is moved. The texture is then updated on screen after a given amount of time. Upon detecting displacement, the mouse sends an HID report that is handled by low-level layers of the operating system before getting out of the HID stack. So here we can do another measure. Then upon notification of the operating system then processes the event and applies the transfer function to move the system pointer. So here we can do another measure. And upon notification of this pointer movement, the toolkit creates an event. We can do another measure and dispatches this event to the appropriate widget. It's where we get the mouse move event. So the end-to-end latency we measure is the time elapsed between the window repaint and the mouse move event dispatched. So using the method, we compare different toolkits on the same machine. So each time we did 1,000 measures. And results show substantial differences between GLUT and swing or Huot in terms of mean latency. For instance, for GLUT, there is 20 milliseconds less latency compared to Java Swing or C++ Huot. We have comparable standard deviation between the toolkits. And so in the three cases, the latency between the HID stack and the mouse move event in the toolkit is around 1 millisecond. So at the beginning, we expected that, for instance, with Java Swing, it would take more time, but it was not the case. So thanks to the repeated measures, we can also see the distribution of latency. So this plot shows a clear difference between swing and Huot, so the two bottom pictures. And this is certainly due to a scheduling system in Huot. But to really explain the differences between the toolkit, we have no definitive explanation. We measured end-to-end latency on different operating systems and web browsers on the same machine. So all the details are in the paper. We also investigated how the system load can affect the latency using stress tests. And we show it increases the mean latency, but also the latency jitter. And again, we can show that because we can easily do repeated measures. So to conclude, we presented the first method to do repeated measures of latency in real time. And we have shown substantial differences between API. On average, the end-to-end latency is around 70 milliseconds on a high-end computer doing nothing. And it is known that above 50 milliseconds for indirect interaction, latency can affect performance. The main limitation of our technique is that it does not work with laser mice. We have a website with an interactive demo. Maybe you have shown the interactive demo on Monday evening. You can go on this website and try the interactive demo with your own machine and your own mouse. And so last, now you have no more excuse for not measuring and reporting latency, especially if you do some physical experiment, for instance. Latency can be a confounding factor in the experiment. So we think it's important to report it so that other people can replicate your result and explain possible differences. So thank you for your attention.
So I have a short question, and you hinted at that at the very end here. So we can't do anything about the latency, I don't think, or maybe we can. So beyond reporting it, is there any other strategies that, if I'm running an experiment or designing an interaction technique, that I can do, you know, with this in mind?
So at least you can choose the right API to do your experiment. Because you have shown, for instance, with GLUT, you have 20 milliseconds less latency. Or if you want, for instance, to run your experiment in a web browser, at least you know, okay, it increases latency, but at least you know how much. So, now you can do informed choice about latency and also latency jitter.
Give you another moment. Any questions? Remember, it's important to ask questions to our speakers, so show that you're engaged. I have another question, so I can do it. Okay. This is a hard one, too. So, and maybe while I'm asking this question, James, you can set up. So one interesting part of this project is you're measuring using an internal clock. So the same system that you're measuring is the system you're actually using to time the measurement. Can you talk about why that's... It's typically not. It's not a typical technique or typical methodology.
That's true. So usually we rely on an external clock. So here we use the clock of the system that can be very accurate, and this way we can do intermediate measures of latency. So it can be possible with an external camera, but it's very, very difficult.